Good day to all of you. So far we have covered this chapter of fire. We have covered the topics of explosions and talk about the calculations of how to calculate the flammability limits and also the potential impact of an explosion. In this week, this chapter 7, we are going to cover about the preventions method for all these fire and explosions to happen. As we mentioned before, the organic solvents are the most common source of fires and explosion in the chemical industry. And also to prevent it, we must be familiar with the fire and explosion properties of material, which we already covered in the last 2 weeks chapter, and also the natures of fire and explosions processes. So this week topics is mainly on the procedures to reduce the fire and an explosions hazard. There are three main elements that we cover in this chapter. First is to prevent the flammable mixtures by reducing the flammability, meaning we put that chemicals or mixtures of chemicals to be either below the flammability limits or above the flammability limit so that it cannot burn, or we prevent the ignitions of the fires or the explosions. Means we prevent it from the source of happening. The next thing is if we can't prevent the first two, then our job as an engineer is to look at the potential to minimize the damage after a fire or explosions that has occurred. The strategies to prevent fire and explosion is presented in these chapters, and the topics that how we can implement it is include inerting, the use of flammable diagram, static electricities, controlling static electricities, ventilations, explosion-proof equipments and instruments, sprinkler systems, and also miscellaneous design feature for preventing fire and explosion. Inerting is one of the process by adding inert gas to a combustible mixture to reduce the concentrations of oxygen below the limiting oxygen concentrations, the LOC. The inert gas is usually nitrogen or carbon dioxide, although steam is sometimes used. For many gases, the LOC is approximately about 10%, and for many dust, that's about 8%. Inerting began with the initial purge of the vessels with an inert gas to bring down the oxygen concentrations to a safe concentrations. A commonly used control point is 4% below the LOC, that is 6% of oxygen if the LOC is 10%. There are several purging methods used to initiate the reduce of oxygen concentrations to the low set point, such as vacuum purging, pressure purging, combined vacuum pressures purging, vacuum and pressure purging with impure nitrogens, etc. Below the limiting oxygen concentrations, the LOC, the reactions cannot generate enough energy to heat the entire mixture of gases, including the inert gases, to the extent required for a self-propagation of the flame. The LOC has also been called the minimum oxygen concentrations, MOC, the maximum safe oxygen concentrations, MSOC, and other names. The LOC has units of percentage of moles of oxygen in total moles. If experimental data are not available, the LOC is estimated using the stoichiometry of the combustion reactions and the LFL. These procedures work for many hydrocarbons. The following equation shows us the LOC calculations where it starts from the mole of oxygen from the stoichiometry with the calculations of the moles of fuels. In other words, it's actually the LFL times the total mole of oxygen over moles of fuels. So you can see from this the equations down here, which LOC equals to this whole thing that you can actually just times in the value. First, let us look at the example to calculate the LOC. So estimate the LOC for butane, and we know that butane stands for C4H10. So we want to know if, let's say, this is a combustion reaction. Okay, means add O2 and it produces CO2 plus X amount of H2O. So with all this, so 4 here, you get 4 CO2 out and H10, so you will have 5 molecules of H2O. So if, let's say, we calculate how many mole of oxygens, there will be 4 here and another 2.5 here. So it will be 6.5 mole of oxygens. Okay, so we also want to know what is the LFL of butane. So you can get this from the table, okay, and you find it from Appendix AB. You will find that the LFL for butane is actually 1.8 volume percent. Okay, so the formula is LOC equals to LFL times the oxygen's moles over total mole of fuels. Okay, so in this case, what we have here is 1.8 times, here we have 6.5 over total 1 mole of fuel here. Okay, so if you calculate this out, it will be 11.7 volume percent of oxygen. So meaning the limiting oxygen's concentrations for 1 mole of butane is 11.7 volume percent of oxygen. As we mentioned earlier, the commonly used control point for purging is the 4% of below LOC, and meaning so if it's for 10%, we purge it until it reaches 6%. And in the next few slides, I'm going to show you what sort of purgings that we can use for us to calculate this value. Vacuum purging is one of the most common inerting procedures for vessels. And this procedure is not to be used for large storage vessels because they are not usually designed for vacuum and can only withstand the pressures of only a few inches of water. However, if we are talking about vessels here, like reactors are normally designed for a full vacuum that is about -760 mmHg gauge or even 0 mmHg absolute. Consequently, the vacuum purging is a common procedure for all reactors. The steps in the vacuum purging process include drawing a vacuum on the vessels until the desired vacuum is reached, then relieving the vacuums with an inert gas such as nitrogens or carbon dioxide to the atmospheric pressures, and then repeat step 1 and 2 until the desired oxygen's concentrations is reached. So you can look at this graph here. The initial oxygen concentrations under vacuum is started with the Y0 here. So what happened is that we put in a vacuum system, we vacuum it or it comes down to a level that the vessels can take it. Then over here, we let it saturated, or we let it sit down for a while. Then we start to purge or include inert gas at these pressures and go so that it can go back up to the original pressure. And we let it sit for a while. And the next thing is we again remove or vacuum the vessels so that the pressures can come down to, again, the lower pressures that the vessels can take. and again, and we repeat this process again and again until this LOC level is achieved. Another way to do this is that vessels can also be pressure purged by adding inert gas under pressure. After this added gas is diffused through the vessels, it is then vented to the atmosphere, usually down to the atmospheric pressure. And more than one pressure cycle is needed to reduce the oxidant's content to the desired concentration. So it normally started with the atmospheric pressure, and then we purge in inert gas to a higher pressure. We let it mix, and we let that inert gas mix with air. Then we slowly release that gases to the atmospheric pressures again. And assuming during this release, the concentrations in the vessels remain. So meaning because we add in more inert gases here, so our oxygens reduce. And when it comes back down to the atmospheric pressure, we let it sit for a while. And we continue to push a second cycle of inert gas into the vessel to the higher pressures that it can take, it can withstand. And we let it mix, sit for a while, and again release the content of the tank back to the atmospheric pressure. So every cycle, the oxygen's content is reduced because of the inert gas additions in the vessels itself. So during the depressurization process, the compositions of the gas within the vessels are actually remain constant, but the total number of moles is reduced. So the oxygen's mole fractions remain unchanged during these pressure release sessions. Okay? And we repeat these cycles until again the desired LOC is reached. One of the practical advantages of the pressure purging versus vacuum purging is the potentials for cycle time reductions. The pressurization process is much more rapid for this pressure purging compared to relatively slow process of developing a vacuum. And also, the capacity of a vacuum system decreases significantly as the absolute vacuum is decreased. Pressure purging, however, uses more inert gases. Therefore, the best purging process is selected based on the cost and the performance. A common ignition source within the chemical plants is sparks, resulting from static charge build-up and a sudden discharge. Static electricity is perhaps one of the most elusive of ignition sources. Despite considerable efforts, serious explosions and fire caused by static ignitions continue to plague the chemical process industry. The best design methods for preventing this type of ignition source are developed by understanding the fundamental relevance to static charge, and also by using this fundamental to design specific features within a plant to prevent the accumulations of static charge, or to recognize situations where the buildup of a static electricity is inevitable and unavoidable. For unavoidable static buildup designs, features are also added to continuously and reliably inert the atmosphere around the regions where static sparks are likely. Common industry examples are such as pumping a non-conductive liquid through a pipe, mixing immiscible liquid, numerical conveying solids, leaking steams that contact an ungrounded conductor. So all this static charge in this example accumulates to develop large voltage. Subsequent grounding produce large and energetic sparks.
We continue to follow this breaking news out of Valley Center this morning. A huge explosion.
Tremendous amount of heat, smoke.
Officers and authorities are worrying about getting traffic rerouting, getting people out of the area.
On July 17, 2007, at about 9 a.m., an explosion in a flammable solvent storage tank at the Barton Solvents facility rocked the town of Valley Center, Kansas, about 15 miles north of Wichita.
This is no longer a safe area. They're requesting that you evacuate.
After the explosion, the fire spread, igniting the contents of other storage vessels and eventually destroying the entire tank farm.
The CSB issued a case study on the accident. Our goal is to help companies understand the hazards associated with the kinds of flammable liquids that were stored and transferred at Barton Solvents.
At Barton, several factors combined to produce the initial explosion. Our investigation shows the need for companies to take extra precautions when handling what are known as non-conductive flammable liquids, which tend to accumulate static electricity. Based on equipment testing, laboratory analysis, and interviews and documents, here's what the CSB believes most likely happened on July 17, 2007.
Barton Solvents was located on the edge of a residential community. The facility was a wholesale distributor of solvents and other industrial chemicals, which were stored in large outdoor tanks. About 8:30 on the morning of the accident, a tanker trailer arrived to transfer a non-conductive solvent known as Varnish Makers and Painters, or VM&P naphtha, into a storage tank. Because liquid flowing through pipes and valves generates static electricity, which can ignite flammable vapor, the tank farm supervisor connected a cable between the truck and an electrical grounding station. In addition, all the equipment involved in transferring the liquid was bonded, that is, connected together with electrical conductors and grounded. Inside the 15,000-gallon storage tank, there was a device for measuring the liquid level. A metal tape, which was grounded, was suspended from pulleys and connected to a metal float by a loose, flexible linkage assembly. This linkage presented a hidden danger during the filling of the tank. The solvent was pumped from 3 tanker trailer compartments into the tank. As the hose was switched from one compartment to another, air entered the line, creating bubbles and turbulence inside the tank. A static electrical charge built up in the non-conductive liquid. Meanwhile, the space above the liquid was filled with an explosive mixture of vapor and air. The swirling, turbulent liquid caused the float to drift and rock, creating slack in the metal tape. This allowed a gap to form intermittently in the linkage assembly, interrupting the grounding of the float. The metal float accumulated a static electrical charge. About 9 a.m., a spark from static electricity ignited the vapor-air mixture, causing a massive explosion. The blast sent the storage tank rocketing into the air. 2 more tanks quickly ruptured and released their contents into the rapidly expanding fire. As the fire raged inside the tank farm, other tanks burst and ignited, launching heavy steel tank lids 10 to 12 feet in diameter into the air. 20,000 gallons of flammable liquid were released into the spill containment area. Valves, pipes, and other heavy steel objects were hurled off-site and into the adjoining community. 1 tank lid struck a mobile home about 300 feet away. A pressure valve hit a neighboring business 400 feet away. 6,000 residents were evacuated. 11 residents and 1 firefighter required medical treatment.
When transferring flammable liquids, it's standard industry practice to bond and ground storage vessels, tankers, and other equipment to prevent static discharges. But our investigation illustrates how normal bonding and grounding may not be enough to prevent ignition from static electric sparks.
Our investigation found several conditions likely increased the accumulation of static electricity inside the storage tank at Barton.
The CSB concluded that repeated starting and stopping of the pump, air in the transfer piping, and the likely presence of water and sediment in the tank all contributed to rapid static charge accumulation. Because VMP naphtha is a poor conductor of electricity, the static charge accumulated faster than it could dissipate, even though the tank itself was grounded.
A lot of common flammable liquids are particularly susceptible to ignition by static sparks. At normal temperatures inside a storage tank, they can produce the optimal amount of vapor to fuel an explosion.
That's not so with gasoline, which is highly volatile and usually produces a vapor-air mixture that is too rich to ignite inside storage tanks. But the CSB noted that less volatile liquids, like VMP naphtha, hexane, heptane, toluene, xylene, and benzene, form vapor-air mixtures that are within the flammable range and can ignite readily.
Because most material safety data sheets do not communicate all the hazards of non-conductive flammable liquids, the CSB recommends companies take additional safety measures when handling these materials.
The CSB said companies should consider purging storage tanks with an inert gas to remove oxygen, adding anti-static agents to non-conductive liquids, pumping liquids more slowly, and contacting manufacturers for additional safety information that may not be found on MSDSs. And the CSB case study also urges special precautions for tank-level floats that have a loose linkage assembly like the one at Barton. Companies should replace or modify these floats so that they remain properly bonded and grounded at all times. The CSB cautioned that while the most likely cause of the Barton explosion was sparking across the float linkage, explosions can occur in tanks without floats when there is a static discharge from the liquid itself. Companies should consult the CSB case study and its references for additional information.
The CSB determined that the material safety data sheet for the solvent involved in the explosion did not adequately describe the explosive hazard or the precautions necessary to prevent ignition from static electricity.
Material safety data sheets, or MSDSs, are required under federal OSHA regulations to warn workers about the potential hazards from chemicals. The MSDS for the naphtha supplied to Barton indicated the solvent could accumulate a static charge, which could spark and ignite vapor. But the MSDS did not warn that the naphtha could form a highly flammable vapor-air mixture inside a storage tank. And apart from normal bonding and grounding, the MSDS did not include any special precautions against static ignition. CSB investigators said the lack of warnings reflected a broader problem.
We reviewed material safety data sheets for 62 non-conductive flammable liquids that are widely used in industry. The CSB found that the vast majority of these MSDSs had significant gaps.
Of the 62 MSDSs covering a number of widely used non-conductive liquids, most failed to recommend specific precautions beyond bonding and grounding to prevent static sparks. Only 3 included electrical conductivity testing data, and only 1 of the 62 MSDSs warned of the danger of an ignitable vapor-air mixture forming inside a storage tank.
The CSB recommended that OSHA improve the information required in material safety data sheets for non-conductive flammable liquids.
The CSB recommended that OSHA advise MSDS preparers to evaluate each product to determine its potential for accumulating static electricity and to form an ignitable vapor-air mixture inside a storage tank. Each liquid should be tested for electrical conductivity, and the results included in the MSDS. The CSB also recommended that 6 major oil and chemical industry associations ask their member companies to improve the warnings on their MSDSs for flammable liquids that can accumulate static electricity.
We hope the CSB investigation helps increase awareness about the hazards of non-conductive flammable liquids, so accidents like the one at Barton Solvents will not be repeated. Thank you for watching this CSB safety video. For more information about the CSB investigation and to view the case study on the accident, please visit our website at csb.gov.
There are several ways to control the static electricities. One is to prevent charges from accumulations, and the other one is once we have these charge accumulations, the next thing we want to do is to discharge them to the ground. But before that, it is important for us to understand the charge accumulations processes. So far, there are a total of 4 charge accumulation processes that are relevant to dangerous electrostatic discharge in a chemical plant. The first one is what we call the contact and frictional charging. It happens when two materials, with one being an insulator, are brought into contact. A charge separation occurs at the interface. If the two objects are then separated, some of the charge remains separated, giving the two materials opposite but equal charge. Second is what we call a double layer chargings. The charge separations occur on a microscopic scale in the liquid at any interface, meaning solid liquid, gas liquid, or liquid-liquid interface. As the liquid flows, it carries a charge and it leaves a charge of opposite sign on the other surface, for example, a pipe wall. The next charge accumulations is what we call induction charging. This phenomenon is applicable only to material that are electrically conductive. A person with insulated shoes, for example, may approach an overhead vessel that is positively charged, which is previously filled with a positive charged solids. Electrons in the person's body, the head, the shoulders, or arm, migrate towards a positive charge of the vessel, thus an accumulating of equal quantity of positive charge on the opposite side of the body. This leaves the lower part of the body positively charged by induction. When the metal object is touched, then there will be a transfer of electrons, creating a static spark. The last one is what we call charging by transport. When a charged liquid droplets or solid particle settles on an isolated object, the object is charged. The transfer charge is a function of the object's capacitance and of the conductivities of the droplets, particles, and interface. The design objective is to prevent the buildup of charges on the product, be it the liquid or powder, as well as on the surrounding objects, the equipment or the personnel. For every charged object, there exists of its oppositely charged counterpart. These methods are used to achieve this objective by preventing charges from accumulating to dangerous level by first reducing the rate of charge generations and increase the rate of charge relaxations. This method is generally used when handling liquid. The other one is by designing the system to include charge reductions by means of low energy discharge. This method is generally used when handling powder. But when a dangerous discharge cannot be eliminated, then it is important to prevent the possibility of ignitions by maintaining oxidant level below the combustible level, by being inerting, or by maintaining the fuel level below the LFL or above the UFL. These are the special design features for preventing electrostatic ignitions. For example, for sparks are prevented by grounding and bonding process. This procedure prevents two metallic objects close to each other from having different potential. Grounding and bonding are used especially to prevent the existence of isolated metal parts or objects. Isolated objects are notorious for building up large potentials and energetic sparks when they are approached by another conductor at a lower potential. Propagating brushes discharge are used to prevent keeping the non-conductive surface or coating thin enough or conductive enough to have a breakdown voltage below 4 kW. These discharges are also prevented by keeping the metallic backing grounded to eliminate the accumulations of a higher density charge on the metallic interface and the counter charge on the non-conductor surface. There are also other discharge methods that you can study on your own, such as the Consell Pile, brush discharge method, or even they call it the lightning light discharge method, by preventing or by keeping the vessel volume less than certain amount. All electrical devices are inherent ignition sources. Special design features are required to prevent the ignitions of flammable vapor and dust. The fire and explosion hazard is directly proportional to the number and type of electrical power devices in the process area. Most safety practices for electrical installations are based on the National Electric Codes (NEC). Although states or insurance company may have their own installations requirement, they are usually based on the NEC. Process area are divided into two major types of environment, the XP and the non-XP. XP stands for explosion proof, meaning flammable material, particularly vapors, might be presented at certain time. The non-XP means that the flammable materials are not present, even under abnormal conditions. For non-XP design areas, open flame, heated elements, and other source of ignitions may be present. So, the designs of electrical equipments and installations is based on the natures of process hazards or specific process classification. The classifications method is defined in the National Electrical Code, and it is a function of the natures and degree of process hazard within a particular area. And the rating method includes Class 1, Class 2, Class 3, Group A to G, Divisions 1 or 2. Like shown in these slides, the Class 1 means flammable gases and vapor, Class 2 are for dust, Class 3 are for fibers, but not likely to be in suspensions. Or some they even group it like Group A is acetylene, Group B is hydrogen ethylene, Group C are carbon monoxide, etc. When it comes to designing for an explosion-proof areas, all pieces of electrical equipment and instrumentations are specified for the class, the groups, and the divisions as discussed earlier. So all pieces of these equipment and instrumentations within the area must be appropriately specified and installed. The overall classification is only as good as the piece of equipment in an area with the lowest classification. Other than this, proper ventilation is also another method to prevent fire and explosions. The purpose of ventilation is to dilute the explosive vapors with air to prevent explosions and to confine the hazardous flammable mixture. Since we talked about proper ventilations, there are two types of plants or chemical plants. One is the open air plants, and open air plants is highly recommended because of the average wind velocities are usually high enough to safely dilute volatile chemical leak that may exist in a plant. Although safety precautions are always practiced to minimize risk, but however, accidental release from pump seals or other potential release points still happen. However, frequently, processes cannot be constructed outside. So if let's say we have a plant to have to be built inside a building, in this case, local and dilutions ventilation system are required, as we discussed earlier in Chapter 3, Industrial Hygiene. Local ventilation is one of the most effective methods to control flammable gas release. Dilutions ventilations, however, is also being used because of the potential point of release are usually very huge, and it may be mechanical or economically impossible to cover every potential release point with only local ventilation. Lastly, but not the least, that sprinkler systems are an effective way to contain fires. The system contains of arrays of sprinkler heads connected to a water supply, and the heads are mounted in a high locations, usually near ceiling, and disperse a fine spray of water in an area when activated. The heads are activated by a variety of methods. The common approach of activations the heads individually by melting of a fusible link holding a plug in the head assembly. Once activated, the sprinkler cannot be turned off unless the main water supply is stopped. This approach is what we call a wet pipe system. These systems are normally used for storage area, laboratories, control rooms, small pilots area. Another approach activates the entire sprinkler arrays is from a common point control point. The common control point is then connected to an array of heat or smoke detector that start the sprinklers when an abnormal condition is detected. If a fire is detected, the entire sprinkler arrays within that area is activated, possibly in areas not even affected by the fire. This approach is called a deluge system, and the system is used for plant process area and larger pilot plants. Sprinkler system can cause a considerably water damage when activated, so depending on the content of the building and the process structures. Statistically, the amount of water damage is never as great as the damage caused by fire in the area, and therefore sprinkler is still an important system to reduce the fire damage.